Why are S-plane poles and zeros important for electrical transfer functions? Have you ever wondered how electrical systems respond to different inputs? Understanding the role of poles and zeros in the S-plane can help clarify this. Let's break it down. In electrical engineering, transfer functions describe how systems react to inputs in the frequency domain. The S-plane is where we analyze these functions. Here, the variable S combines real and imaginary parts. The real part represents exponential decay or growth, while the imaginary part relates to oscillation frequency. Poles are specific values of S that make the denominator of the transfer function zero. When this happens, the output of the system can theoretically become infinite. On the other hand, zeros are values of S that make the numerator zero, resulting in an output of zero at those frequencies. Together, poles and zeros shape how a system behaves in terms of frequency response and stability. One key reason why S-plane poles and zeros matter is system stability. The location of poles indicates whether a system is stable or unstable. If a pole has a positive real part, it means the system is unstable, causing outputs to grow exponentially. Conversely, poles with negative real parts indicate a stable system with decaying responses. Poles on the imaginary axis suggest marginal stability or sustained oscillations. Another important aspect is how poles and zeros shape frequency response. Poles tend to reduce the magnitude of the output and introduce a negative phase shift near their frequencies. Zeros do the opposite. They increase magnitude and add positive phase shifts. This interaction is vital for defining filter characteristics, such as cutoff frequencies and resonance. Transient response is also influenced by poles. The real part of a pole relates to how quickly a system responds, while the imaginary part indicates the frequency of oscillation. Zeros can affect how this response starts, creating phase lead or lag effects. Engineers use pole zero plots to design controllers, compensators, and filters. By placing poles and zeros in specific locations in the S-plane, they can tailor a system's behavior to meet desired specifications. This includes aspects like stability margins and speed of response. Additionally, representing transfer functions in terms of poles and zeros simplifies analysis. It allows for easier mathematical manipulation and provides a clearer understanding of system behavior without directly solving differential equations. The geometric view on the S-plane helps visualize how the system reacts at different frequencies. Lastly, poles and zeros relate to physical components in electrical circuits. For instance, in a resistor-capacitor low-pass filter, the pole defines the cutoff frequency. In summary, S-plane poles and zeros are essential for analyzing and designing electrical systems. They help engineers assess stability, frequency response, and transient behavior effectively. Understanding their roles can lead to better control and design of electrical systems.